Okay, well, let's get going. So, first of all, I'll give the same disclaimer that Ralph gave. Right? So, what the story I'm going to give you going to be, I will try to give you an overview of the field, but it won't be very complete. It won't be very homogeneous. Right? And also because I presume you all have very, very different backgrounds. So, some things I'm going to say, for some of you, you will know that. Some of you won't. And so, if I'm just saying something really simple that you all know very well, just check your email or take a snap, whatever. Then, in terms of style, anytime I'm coming from the other side of the ocean, so there they have a very different style of lecturing. Like here in Europe, especially in Germany, the professor is a god and students are reverent listeners. In America, students are dignitaries and a professor is a paid entertainer. So, first of all, if you want to interrupt and ask a question, just raise your hand and feel free to interrupt me. And then I also prepared a few quizzes because it's supposed to be actually a course, right? So the story I'm going to tell is the overview of the whole, sort of the main storyline. Is how gas gets into galaxies and what it does there. Right? So when we will get to the point where the gas gets into galaxies, there may be some overlap with what Ralph is saying. We will try to coordinate with him. We haven't done it yet. But even if we talk about the same stories, the same topic, both of us talk about, then we will be talking from two different perspectives. So I treat star formation as a user, right? So I don't actually need to understand how it really happens, just like this laptop. I don't really understand what happens inside this motherboard, but I can use it. So the same attitude towards star formation feedback. I need to understand how to use it. I really don't care how it happens. And so Ralph actually cares how it happens. So some of the topics that we cover and where we overlap, we will have different perspectives. And as finally, as I said, to be very uneven depths on different topics because the whole subject is very large. There's no way I can cover it all in depth, and I don't know everything myself. And so that will be very uneven depths in different subtopics. And of course, it will be biased in my personal interest. So I roughly divided into 5 different parts. So the first one is IgM, second one is CGM, circummolecular nuclear medium, then ISM, and star formation feedback. But the boundaries between those sort of topics are kind of vague. So we start with IgM. And before we go, I want to make sure that we're all on the same level of ground. Again, I don't know what background all of you had, and I suspect it's very diverse. So you all presumably know that the universe expands. And the expansion rate is determined by the Hubble parameter, which in standard lambda CDM depends on 4 cosmological parameters, out of which one is supposedly very small. So this is standard cosmology. We are going into detail. Walker talked about what A stands for. We also know the densities fluctuate. So the delta is the cosmic overdensity that measures the amount of density above or below the mean cosmic density. And in the linear regime on large scales, where you can ignore second order corrections when delta is very small, then they go uniformly within time. So the equation that govern the rate of growth of linear fluctuations in standard cosmology is the second order differential equation. And none of those terms, except, well, there is something happening here on small scales. But if you forget those small scale terms, which I'll talk about later, these terms don't depend on x, which means that at every point x, they grow with the same rate. So we can write the equation for the meta overdensity, and actually for a good reason, I didn't put any subscript here, as you will see in a few minutes why I didn't do that. But if you take the meta overdensity total, take dark matter and baryons and whatever else, neutrinos, whatever else exists, spaceships from parallel universe, whatever, if you all combine it together, and all those fluctuations in density grow with the same rate, independent of the spatial location. So these two-dimensional dependence can be separated into a function of time and function of position. And presumably most of you know that. And again, this function of time is called the linear growing mode. And it is not uniquely defined because I took one function and actually separated into two. So the normalization of this linear growing mode is actually ambiguous. And there are two different ways people usually normalize it. So just be aware of that it may have different normalization, but it's the same functional form. So in general, it's not an analytical function of time for general lambda CDM cosmology. At very early times, when a scale factor is much less than 1, the expansion rate is dominated by matter and radiation. Right? So for this type of expansion, you can solve this analytically, and then it's equal scale factor plus some constant term, which depends on the ratio of matter and radiation. And there is other very long expression that's only important at redshifts, which are not subject of our discussion this week, right, at very high redshifts. So because fluctuations in lambda CDM are generated during inflation, and they are produced from quantum noise, and quantum noise is incoherent, which means that they are Gaussian. Right? So the phases of two different waves in the fluctuations are not correlated. So the Gaussian random noise is described entirely by one-dimensional function. Right? It's either the correlation function or the power spectrum, the Fourier transforms of each other. You know one, you know the other. All you have to do is take the Fourier transform. So if I go into Fourier space, which is convenient in all linear analysis, not only in cosmology, but in any field, and so I take delta and I Fourier transform it into delta sub k, then the Gaussian random field means that if I have two modes with two different wave vectors k, they are not correlated. So the average, if I now average over all possible universes, but in practice means I take some volume and average over different realizations of this volume, then this average is proportional to Dirac delta function. So it's 0 when k1 is not equal to k2, and when they're equal, it depends on the power spectrum. And so this P of k is this one-dimensional function power spectrum that determines everything you need to know about this, everything there is to know about this Gaussian random field. And so the power spectrum for standard cosmological models, I'm sure you've seen too. Right? So because delta grows as d plus as a function of time, and the power spectrum, which is square of delta, goes as d plus squared as a function of time times some p naught, which depends only on wave number k, doesn't depend on time. So for standard cosmology, this is value of p naught. Again, there is some ambiguity in normalization. Remember this. So the numbers may move up and down depending on how different people used to normalize it. But this is standard spectrum. So it's close to +1 on large scales. This is Harrison-Ledovich spectrum from inflation, slightly shallower than n equal 1. Then it has a peak at about 0.02 on k. Right? And then there's this bumpers and wiggles, which are baryonic acoustic oscillations. Again, I presume many of you heard about this. And then it falls off very, very gradually. It falls off so gradually that eventually at very small scale, so if we go to the second -2 floor, it will be about -3. Right? But over a very large range of these two resonated and wave numbers, it's actually -2. Right? Very close to -2. And then it very rapidly goes from this +1 to -2. It goes in less than a decade, essentially, in the wave number. Again, there's a standard spectrum which you can compute using any standard linear gravity code like CAMP or CMB fast or anything of this sort. So remember that the power spectrum is a square of the amplitude per mode. Right? But if we go to large wave numbers, the volume in wave space grows as k cubed. So if you now compare not only the power per mode, but the power per unit k, which is a absolute value of the vector. So the larger the vector, the larger the sphere in which it can move around. So then if you compare the power per actual log k, and sometimes people use this k cubed times p of k. So it's a power per log absolute value of k. This has a very different shape. It grows with k. And at a large k, it grows logarithmically, but for a large range of k, it goes roughly as k to the minus to the first power. Right? But it continues increasing to small and smaller scales, and if you go further, then there'll be some bumps and wiggles there at different times in the history of the universe, but it's a different story. And then talking about standard cosmology. But I assume that you all know this, and then if you don't, then just go somewhere on Wikipedia and tonight, and instead of skiing just today, and make sure we are in the same ground. Right? Otherwise, you misunderstand what I'm going to, or actually won't understand what I'm going to talk about. And finally, this theoretical power spectrum which we can compute, right? And for lambda CDM model has a large number of observations in different methods. Right? There's CMB, galaxy clustering, Raman forest, etc., etc. And you see that we can probe the spectrum over 4 orders and lengths. And that's why we are now in the era of precision cosmology, because now we can constrain this power spectrum and the cosmological parameters on which this power spectrum depends to reasonable precision. Okay, so that was like an introduction, starting point. So I assume you all know that, or at least you should know that. Right? So now we go to the actual part of my first part of my lecture, talk about baryons. So what do baryons do on large scales? So universe contains baryons that we all know, if you can touch yourself if you doubt that. Right? So the density of baryons on average is 2.5 times 10 to the minus 7 today, and of course the scale is 1 over 8 cubed because baryons are conserved. So at early times the density is higher. We know that primordial abundance set by Big Bang nuclear synthesis is 70% hydrogen and 24% nuclear, helium. And of course, later, as stars start shining up, we get a little bit of heavy elements. The difference between, on large scales, the difference between gas and dark matter, that gas has pressure. And now I go back to the equation I already wrote, right, for linear growth rate. Now I start putting indices to that. So X means dark matter because we don't know what dark matter particle is. So I like to put X for dark matter. So this is the same equation I showed before. This is the rate to which fluctuations of dark matter grow in linear regime. And this is, of course, the total matter. It's a fraction of stuff in dark matter times fluctuation in dark matter plus the fraction of matter and baryons times the fluctuation in baryons. And you can write the same thing for baryons. And the gravity, of course, will be the same. This is just the expansion terms. But because baryons have pressure, they have this one extra term here. This is a pressure force due to gas pressure in linear regime. So it depends on, of course, fluctuations in baryons. If there is no fluctuations, if baryons are completely uniform, there is no gradient in pressure, there is no force. Right? The sound speed tells you how much pressure you have. And in terms of spatial dependence, it depends on k squared. So this term is only large, is only important when k is large, which means small scale. Like k is a wave number, the 1 over scale. So we can now look at those two equations, and they already tell us how baryons and dark matter behave in the linear regime. Right? So I can take these two equations, put them on the computer and solve them, and for some histories I get something like this. So in this plot, ignore all the symbols. Right? The symbols, I was just too lazy to redo the plot. So what I actually want to show is just this line. So this tells you the ratio of baryonic fluctuations versus dark matter fluctuation as a function of wave number at some reasonable time. So it's about redshift 3, I think, if I remember correctly. So on large scales, it goes to 1, which means the baryons trace dark matter. So the fluctuations baryons are the same fluctuations dark matter in relative terms. Right? There's less baryons, but the delta is the same. But then on small scales, they go down because of this negative pressure term, which suppresses fluctuations. And so fluctuations go down, and then they begin to oscillate at some large enough k. So this is a very typical behavior of this ratio. You can do it with different cosmologies, at different redshifts. They all depend, they all look more or less like this, unless you go to very high redshifts more than 10, where things become more complicated. And the higher the redshifts, the more complicated it becomes. So this scale, on which baryonic fluctuation drops below the dark matter fluctuation, describes the rho of pressure in the expanding universe on large scales, not instead on large scales, in the linear regime. So the scale is called the filtering scale. And if you write this relationship mathematically, you can say that at late times, again, redshifts well after 10, and before 10 things are more complicated. the baryons trace dark matter on large scales, but on small scales, they fluctuate less. Right? And so I can take this ratio and say it's 1 when k is very small, and then the next term I can expand in terms of k, because the pressure force depends on k squared. This depends actually in even powers of k. There's no odd powers. And I can write it 1 minus k squared over some factor. Think about this 1 over kf as a coefficient in the front of this term. And of course, there will be other terms, k to the 4th, k to the 6th, etc., etc. And it's also just dropped. So if I write it this way, I can define this scale, which I call the filtering scale. Everyone calls the filtering scale. And it describes the scale over which baryonic fluctuations are suppressed relative to the dark matter fluctuations in the linear regime. So this scale is not the same as the gene scale. That's actually very important. The gene scale is, by definition, is the scale at which this right-hand side is equal to 0. This scale, in fact, is not determined, is undefined in this form because you have fluctuations in dark matter and baryons. So if you actually didn't have any dark matter, only had fluctuations in baryons, this would be 1. Then the k at which this goes to 0 would be the gene scale. Right? So right away you see it's not a very useful quantity because first of all it assumes that there's no dark matter, which is in reality that it dominates. And then as you will see later, it's also just a wrong scale to use. It's not the right value. So the gene scale is a ratio of those two terms, and it may not have anything to do with the filtering scale, which comes up in this ratio. And this ratio comes as a solution to those equations. So our first goal is to understand what this pressure term actually does. So how pressure suppresses fluctuations in baryons in linear regime. So if I write it this way, you can take half an hour, take this ratio, take kf as an arbitrary function, plug it into these equations, then in fact you can solve them. Right? It's a not very difficult exercise. It takes a little bit of time to go through those derivations, but it's relatively straightforward and no tricks. And what you'll get at the end is an expression which looks like this. Right? So I introduce this gene scale so you can see how they're related, but the scale which actually determines where baryons are suppressed, it does depend on the gene scale, but it's not one-to-one correspondence. In fact, it's a very complicated correspondence between one and the other. So very roughly, you can think about this filtering scale as being gene scale smoothed over time, but it's smoothed with very specific window function, right? Which depends on how fluctuations grow and how the universe expands. It turns out that if you put standard lambda CDM, that most of those terms become relatively simpler, significantly simpler. And as a rule of thumb, if you're talking about intergalactic medium at redshifts where it's mostly observed, redshift 2, 3, 4, 5, then as a rule of thumb, this filtering scale as a wave number is twice the wave number of the gene scale, which means that as a spatial scale, it's half the gene's length. Right? And again, this is not an exact relationship, this is just a rule of thumb, because strictly speaking, the gene scale and the filtering scale are related through this integral. And as I said, if you go to early universe, to redshifts higher than 10, things becomes much more complicated. This is the simplest relationship between them that you can find in the literature. The most complicated one would take 2 slides of to present as equation. Just to show you that it actually works in reality, I have these 4 slides from a simulation of IgM at redshift 5, 4, 3, and 2. It shows the contrast of baryonic density, right? So its evolution with time. I don't know if you can see. That's looking close. So the first, what you notice, is of course we have this large curve structure. We have filaments, right? Huh?
Sorry to interrupt. Which of the scale blocks?
I think this is something like 10 megaparsecs. So we see maybe even 5. That's I forgot actually. Sorry. You see these small filaments and again how they evolve. So what you should look at is actually not those filaments because they are present everywhere. What you should look at is this really small, this very faint gray fudges that in fact do disappear with time. Like this one, I think. This one. So the small features that you see in baryonic distribution at high redshift do get erased with time. Sort of. So it's my first quiz. I said there will be quizzes here because it's supposed to be a course, right? Not just lecture. So if you think about what actually happens physically, right? We have dark matter that grows because of gravitational clustering. We have baryons. Right? So, but when pressure dominates, like when you ignore gravity, right? If the only thing with pressure, the only thing pressure does, right? When in this room, for example, pressure force dominates. So if I do this, right, all I do, I'm sending sound waves through the room. So the reason why you don't hear my clap bouncing off infinitely because walls absorb sound. But in space, nothing absorbs sound. In ideal hydrodynamics, when there is no viscosity, sound waves do not dissipate. So they continue going indefinitely. They actually do not get suppressed because sound waves do not dissipate. So why fluctuations baryons are suppressed? So the way I like to do that, I'm sure someone can answer this, but if I just wait for an answer, there will be 1 or 2 people who will be answering those questions, and the rest of you can fall asleep. I don't like that. So what I have is 5 answers. We are going to vote on them. We're going to true American democracy, right, which we impose on the rest of the world with guns and planes, right? Okay, and helicopter gunships. Okay, who's for A? Yeah, have a question? Okay. So that one more thing, right? So I will show several of those quizzes, right? So none of them is truly serious, right? So you should treat them as riddles rather than true quizzes, right? Because of course I wouldn't dare to give you a true quiz, you're not undergrad. So essentially that's a way for you to think, to step back, right, and to think from sort of on a larger scale, like to get the big picture. What is really happening there, and what is the physics that matters? Right? So some of those answers will be completely ridiculous, right? But there is one true one, right? So the first answer, baryons are not suppressed, right? The baryons trace the dark matter on all scales. B, they're suppressed by force of gravity. Angular momentum is conserved. Fluctuations in dark matter grow with time. Fluctuations in baryons decay with time. And there's only one correct answer here. And you can only vote for one. Right? And that's a way for you, first of all, to wake up. And then a nice second to actually try to think what we are talking about, right? To get to not just listen to what I say, but try to really understand what's going on. Okay, who's for A? One. Who's for B? 1, 2, 3. And there's no penalty for wrong answers. 4. Who is for C? No one for C. Who is for D? 1, 2, 3, 4, 5, 6, 7. About 30. Who is for E? Okay, that's about equal. So we have 2 parties now, D and E. Well, the statement, again, I'm not going to go beyond just voting, counting the votes. So the correct answer is actually D, right? And something that's important to understand because I actually use this word several times, that the fluctuations in baryons are being suppressed. It's actually very wrong terminology. They are not being suppressed. Right? This statement is correct. Sound waves do not dissipate. The only reason that this graph looks like this, right, is not because on the small scales this delta gets small. It's because on the small scales this one gets larger. So this one continues to grow with time, whereas this stays the same. That's why these fluctuations are less than 1. As the time goes on, they actually become smaller and smaller than 1, depending how fast this one grows. This one grows with linear growing mode. So if you think about some initial moment, you just switch on the pressure, you can do that in the theory, then you actually start with 1, 1, and pressure fluctuations will go all the way to unity. And as time goes on, they will stay at the same level, because the level was this. Right? But as time goes on, they stay at the same level, but the dark matter will go up. So that's why small scales and very on smooth and dark matter. Only if it goes smoother than dark matter, non-smooth science can stay the same because of pressure prevented growing, not less. So this is actually very common. It's not a mistake, it's just the way astronomical terminology happens. But astronomers are famous for using misnomers all over the place, like trying to the nebula, Big Bang, whatever. Errors and stuff like that. So this phrase that baryons are suppressed on small scales, again another misnomer. They're suppressed relative to the dark matter because dark matter is not suppressed, is not prevented from growing by the pressure force. Okay, so that piece we need to know about what happens on for small fluctuations in dark matter and baryons. So now we go to the next step, talk about ionization. Okay? So if you open the Bible, you know the Bible starts with this phrase, then God said, let there be light. There was light. It didn't say anything about the frequency of this light, but I presume that God was omnipotent, so all frequencies were present, right, when he said that. So if you now consider a region of IgM with some density fluctuations, right? In this case, they don't necessarily be linear. So far we talked about linear fluctuations, but let's consider just arbitrary region with arbitrary density delta. It's still well defined. You can have the density of neutral hydrogen. I often use this notation n sub h, means the density of all hydrogen nuclei, right? So it's ionized, atomic, neutral, whatever it happens, in whatever form hydrogen comes, right? It just means total number density of protons, essentially, in the universe. You can write it again as the average times 1 plus delta. So what we know empirically, and we'll talk about this later a little bit, that at lower redshifts later than 6, the IgM is highly ionized. Right? There's an average, those redshifts like 2, 3, and 4, even actually at redshift 0, there is an average only one neutral atom for 100,000 to a million ionized ions. So IgM is ionized very highly, and again we'll talk about this a little bit later. So in order to keep gas ionized, you need to have ionizing radiation. It's ionized by radiation, not by collisions, because IgM is very low density. So radiation that keeps the gas ionized is called cosmic ionizing background. We are not going to talk about what actually where it comes from. It comes from quasars and stars, and the relative ratio of what comes from quasars, what comes from stars, depends on redshift, and it's actually not very well known. But on average, we know more or less, roughly, we know how much of that there is. At least we know how well IgM is ionized. Right? So if we now write a very simple equation that describes the balance between ionized and neutral hydrogen. So all I have to do is to say, okay, I have my neutral hydrogen, H1 means neutral hydrogen. I presume all of you know this Fermilab notation. So the change in the abundance number density of neutral hydrogen comes from the cosmic expansion. This is just the dilution of density because of expansion of space. Then hydrogen is being destroyed by radiation. So the gamma, the photonization rate, describes the rate with which hydrogen is being ionized. So hydrogen goes from neutral to ionized. But ionized hydrogen can recombine by colliding with the electrons. And so the second term tells you how much hydrogen you get back by having ionized hydrogen H2 colliding with electrons, and happens with some rate. It's called the recombination rate, and in general it's a function of temperature. If I now take the same equation for total hydrogen, I wouldn't have any of those terms because total hydrogen, it's either ionized or neutral, but it's conserved. So if I now take, instead of number density, I use the neutral fractions, the ratio or fraction of all hydrogen which is ionized, then this term disappears because all hydrogen participates in the expansion of space, but only neutral participates in the ionization and recombination, and I get this very simple equation for the neutral fraction. So the rate with which neutral fraction changes is being diminished by the rate of ionization and being reduced by recombination rate. And recombination rate depends on the density of ionized hydrogen, which is 1 minus x, and number density of electrons. So I can take this left-hand side, put it to 0. When my neutral fraction doesn't change, I'm in the ionization equilibrium. My ionizations balance recombinations perfectly. And so this term is equal to that. I can solve for x, and I get this equation. Right? I could have solved it not even exactly, but that's all I need at this point. Because the universe is highly ionized, in fact, I can forget about this minus x for at least a little while today. And then in the ionization equilibrium, I have the neutral fraction. It depends on the ratio of recombination rate and photonization rate. It also depends on the number density of electrons. So if I assume that everything in the universe is ionized, I get 1 electron from hydrogen and 2 electrons from each of the helium. And so I get number density of hydrogen plus twice number density of helium. This is number density of electrons. So maybe we should, okay, you don't see it from the back. I try to use the screen space to the maximum, so I have quite a few equations at the bottom, sorry. So this is number densities at a given point in space. If I factor out that delta, this is the mean density of hydrogen, mean density of helium, and then I get 1 plus delta. It tells me that the neutral fraction growth time goes with density. It's proportional to density in the ionization equilibrium. So denser gas is more neutral, and that's again very easy to understand. The just recombination rate is more efficient because it depends on density squared. You need 2 atoms to collide, whereas for ionization you just have a photon hitting hydrogen and that's it. So nothing very sophisticated here. I presume most of you know that, at least some of you. Okay, so step number 4. You'll see how it all comes together at the end. So let's now talk about line of a forest. And I'll explain what, if you never, who of you have not heard this word before? Everyone, okay, good. So, so if you take a light bulb, right, you put it somewhere in the universe. It can be a quasar, a galaxy, again, a light bulb, anything. And we see it on a cosmic redshift, Z sub E. It's a redshift to which light was emitted. A photon with wavelengths, which it had as a moment of emission, is going to be redshifted. So again, for those of you who know, it's all trivial, just check your email and think about planning your skiing trip in the afternoon. So at lower redshifts, right, this photon will have a wavelength which will be proportional to the ratio of 1 plus z factors. So if I now have a photon emitted in the wavelengths between 1216 angstroms divided by 1 plus z and 1216, that means that for this photon, there is some redshift for which its wavelength at this redshift range is going to be 1216. So maybe I should. All right, so we sit here, we look at light bulb, and we see photons going to us. Right, so the photon, as it leaves the light, gets redshifted more and more until it reaches us. From our point of view, this thing is redshifted at redshift z sub e. From this point of view, we are redshifted at redshift z sub e. Right? And so as photon increases its wavelengths, if its wavelength was below 1216, then at some point as it increases, it can cross some point where its lambda becomes 1216 angstroms. You know what 1216 is. What is 1216? Who knows what 1216 is? 3 people. It's a wavelength of Lyman alpha, right? It's the main line of the main element in this universe. So if you know nothing about spectroscopy, at least you should know Lyman alpha. So this is a wavelength of Lyman alpha. It's a transition from n equal 1 to n equal 2 hydrogen atom. So if we have this photon with this wavelength, means that at some point it redshifts to the wavelengths of Lyman alpha of hydrogen. And then, if you have neutral hydrogen atom that this photon hits, it can excite neutral hydrogen atom from its n equal 1 state to n equal 2. Right? Lyman alpha is the wavelength of this transition. And the photon, of course, will be absorbed because it excites electron, puts it in a higher state. And turns out it does happen. So there's a spectrum of 3.5 quasar, a redshift 3.55 quasar. So this is the wavelengths. This is Lyman alpha of the quasar. That's how we know it's a quasar, because it has this Lyman alpha, which is very broad. This is light that comes immediately from the vicinity of the black hole. This sits in the middle of the quasar. We see the spectrum, which has this very characteristic shape. So you can look at now 30,000 of those quasars, thanks to slow and digital sky survey. They all look the same. They're actually amazingly similar looking. So it has the spectrum. It has a few lines here. But then it has this forest of stuff on the left. Right? And this left are shorter wavelengths, ones which are less redshifted. So if we now look at the anatomy, again, this is Lyman alpha of the photon. This is a signpost, a signature of the quasar. Right? Every quasar that sends light into space puts its signature on the light in terms of this Lyman alpha line. So the red line is actually what the quasar emits. It's called its intrinsic spectrum. Right? This is radiation that actually leaves the accretion disk around the central black hole from which the light goes out. So everything which is difference between black, as the spectrum we observe here on Earth, and the red line is the light which was absorbed on the way from the quasar toward us. So if I now zoom into this piece, right, we see this large number of absorption features. So the blue is what we don't see, right? So the flux which was eaten out by the stuff between us and the quasar. And magenta is what actually still comes to us unabsorbed. So what you need to notice here, first of all, is the existence of this large number of absorption lines, which is called Lyman alpha forest. That is how it was first detected and absorbed and observed. And when the first spectra of high redshift quasars were obtained, it was immediately obvious in 1980s. I don't know when exactly it happened. And another thing that you should notice, as I said, this is a very typical spectrum. You can look at 10,000 of them, they will look almost identical. You'll notice that if I just roughly say, well, what the area is blue, what's area is magenta, oh, it's very crudely 50-50. Maybe it's 30 to 70% or something, but they're comparable. So there's a comparable amount of stuff which is absorbed and a comparable amount of stuff which is transmitted. So remember that. That will be important for the future, and we try to understand why laminar forest, why IgM is highly ionized. So these lines is what's called laminar forest, right? Because it's a forest of very large number. There may be hundreds, if not thousands, of those lines in each individual spectrum, right, of these laminar absorption lines. That's why it's called laminar forest, right, for every quasar. So now if you think about this, it kind of doesn't make sense, right? Because if you take a hydrogen atom and you have an element of a photon, you point it toward atom and hit it. Atom goes to n equal 2 state. It lives there for a tiny fraction of a second, and then it goes back. Right? So because you cannot live forever in the excited state. Right? So when you go back, when the atom goes back, you get this line of a photon back, exactly the same photon. Right? So you cannot actually absorb Lyman alpha radiation. Because you can excite atom temporarily, but then it comes back and you get the photon back. So why do you have absorption? There is a eraser here. So at the end of this lecture, if you don't like those quizzes, you can send me an anonymous email, and then if I get enough of them, I promise not to have them again. Okay, so another vote, right? Another demonstration of American democracy. So do you understand the question, right? So I have a photon, another photon hits the atom goes n equal 2, it sits there for a little while, then it goes back, you get the photon back, right? So you don't actually absorb the photon. Right? So how can there be any Lyman forest if you actually don't absorb the photons? Right? So 5 questions, 5 answers. So it's really an optical illusion. So it's cold in space, so atoms freeze in n equal 2 state. Emission is isotropic. Angular momentum is conserved. an unequal state also decays into photon process, truly destroying Lyman alpha photon. Okay. It's not exactly American democracy because in an American system it should be only 2 answers, right? But here 5. Okay, who is for A? Okay, no one. Who is for B? Quantum mechanics works good. At least you know. Who is for C? Okay, you know that's not fair. Okay. I should have told them those who don't know. Okay, so it's another misnomer, right? I already in one lecture I already used 2 misnomers. It's a suppression of fluctuation by pressure and absorption of Lyman alpha photons. Right? Not really absorption. It's just the fact that when the photon emits, the atom emits the photon, it emits in a random direction, which of course wouldn't necessarily be in the direction of our telescope. So the photon is actually not destroyed, it just doesn't get into the telescope. Right? That's the reason why we don't see. It appears to us as absorption, whereas in reality it's just re-emission in some arbitrary direction in space. Okay. So let's now talk a little bit about getting more sort of boring stuff, talk about atomic absorption. Again, this is standard quantum mechanics of astronomy. Most of you should know that. So again, if you know, just take a break. If you take an atom, right, at rest, that the cross-section for this atom to absorb a photon in the frequency range of nu to nu plus some delta nu, it depends on the atomic constants and then a factor which is called the oscillator strength, and it depends on the Einstein coefficient. So it's a property of a quantum mechanical system that atom is. So you can write this cross-section as a function of frequency as some constant value, sigma naught, which will be different for different atoms in different levels, right? So it's absorption for a given level. And then some function of frequency, which in most general case has this form. And this W is a small atomic constant which is called natural line width, right? So it's a width of the line that atoms will have if they have 0 temperature, don't move at all. Right? So they will still have some width of the line. But very often this one is so small, this quantity W, that you can basically consider the limit of W going to 0, in which case this expression becomes just a Dirac delta function. So if we can ignore this natural line width, we can think that atoms being absorbing and emitting photons at exactly the same frequency, right? Which in reality, of course, it has finite width. But again, it's usually very small. So for Lyman alpha, this cross-section, sigma 0, is called center of the line cross-section. I put it in quotes because it's actually not the cross-section that the line has as a center, as you'll see in the next slide, and the slide after that. Right? So the value it has is 4.8 times 10 to the minus 18. And that's a useful value to remember because most of cross-sections you're going to meet, at least in this first part of this, of course, are all of this order 10 to the minus 18, a few times 10 to the minus 18. So it's a very typical value for many astronomical cross-sections. So, of course, we never observe no single atom, right? Atoms live in large numbers together. So if you have a cloud of gas, let's say you have a cloud of gas with density n and size L. Then we have to integrate this previous expression. This is for single atom, right? We have to integrate over all atoms. So they're all the same, so the same number density L, so it's n times L. Right? It's just path length. Then it's a cross-section, and this function of nu, and then you integrate over all velocities of atoms in this cloud. And of course, atoms move because cloud has some finite temperature. There are a few definitions here that I introduced. So first of all, V prime is actually the velocity of a given atom, and we integrate over all velocities in a Keplerian, in a Maxwellian distribution. This is just Maxwellian distribution. Okay. And I'll show you it in a more familiar form on the next slide. So this nu prime is just the frequency of an atom, frequency of this transition of an atom, which is redshifted by velocity or blue shifted by velocity v prime, right? So this is just Doppler effect. So atoms move with v prime along the line of sight, right? They have frequency of this transition shifted by v prime over c. So this goes from v is a true quantity, nu prime is just derived variable, and then I have this v sub nu, which actually goes this way. So I am observing this at frequency nu, which may nothing to do with the frequency of the transition. I can look at Lyman alpha in the radio, for example. I wouldn't see anything, but I can do that, and I'm allowed. So then I define this v sub nu. It's a different definition of the frequency. I just use the same expression, so I define some velocity that the atom should have for this transition to be in my observed band. And so if I'm looking at the radio, the atom will have to move very close to the speed of light for Lyman alpha to be redshifted into radio. So when I have those two expressions, it's very easy then to use v's together. I just have a simple Maxwellian distribution here, and then this phi depends on nu prime through v, so I have to make this integral, to take this integral. In general case, when I have this, formula for phi, this cannot be taken analytically. It's called a void profile. So there are very accurate numerical approximations to this. You never have to take this integral as an integral. You can just find a fitting formula that works very well. And the limit where this w can be ignored, which is very common in many astrophysical situations, then the integral can be taken, because then phi becomes simply a delta function. And so you don't even have to take the integral, you just take this form. And then what you get at the end is sigma naught NL C over pi over b, and then this minus v squared over b squared. And b is called the Doppler parameter. And if you're familiar with Maxwellian distribution, this is just taking the temperature and all other atomic constants which appear there and just putting them together so this one looks as simple as possible. And again, for historical reasons, astronomers do that. So this is just Maxwellian distribution, nothing else. Right? So now you can see that if I look at the cross-section, so I put it together to have the optical depth, which is, of course, what you measure in the spectrum. But, of course, the cross-section is everything except n and l. So cross-section will be this plus this stuff all together is a cross-section. So if I take now v equals 0, center of the line, my cross-section is c over square root of pi b, sigma naught. So if my c is 300 kilometers per second, 300,000 kilometers per second, and my b is, say, 10 kilometers per second, then this ratio can be huge. And so the actual cross-section of the center of the line is much, much larger than 10 to the minus 18. It's usually 10 to the minus 13 and 10 to the minus 14. Right? So and that's why I put the center of the line cross-section in quotes. Right? It's a useful number because it only depends on atomic constants. It's a fixed number for hydrogen. But the real cross-section for cloud of hydrogen to absorb Lyman alpha radiation at the center of the line is many orders of magnitude higher than that. Right? And depends on the temperature. So the colder the gas, the deeper the line, but the narrower it is. And of course, this n times L is called the Coulomb density, which I presume most of you know that. So we now go back to IGM and to expanding universe. We have to do something slightly more sophisticated, because we actually don't have no separate clouds of hydrogen sitting in the vacuum, right? We have the distribution of gas everywhere. So we have to integrate over all line of sight. So x is a coordinate along the line of sight of the quasar. So dx, what is this? This is comoving length. Yeah, by the way, every time I use x, I grew up with this cosmological connotation. X in cosmology means comoving length. And R means physical. So if you want to confuse all cosmologists, just flip the notation and you just screw up everyone. So x is actually comoving, and 1 plus z, this is dr. This is just the physical length. So all I do, I take this cross-section, take sigma naught times this number density, and I just integrate over dr, over the true physical length along the line of sight, nothing else. But again, as a cosmologist, I have to use x. Otherwise, I would be kicked out of the guild. And of course, redshift does depend on x, because as we move along the line of sight, we get more and more redshifted. So number density will depend as a function of x, because we have fluctuations in the universe. The velocity, again, will depend, because gas will move at different velocities in different positions. We also have the redshift. And then the wave length at which we observe this, and I'm switching from frequency to wavelengths, because in Lyman alpha forest, historically, astronomers, observers used wavelengths as a measurement rather than frequency. So when we get to the wavelengths, it's a wavelength of Lyman alpha, 1216. Then there's a redshift at the position of x plus this peculiar velocity of atoms at the position of x. So at some distance from us, the universe expands with redshift z, but then atoms, they also move back and forth. So we have these two contributions to the redshift, the cosmological redshift, to the local Doppler effect. So when I'm supposed to finish? Not now. Okay, so let me give me this example. Okay, I went much lower than that, so I'm afraid I'll have to stay for another week. So this is just an example of Lyman alpha forest from the simulations. Right? So this is actually a real cosmological simulation of Lyman alpha forest from about 96 when it first appeared. So there are two things, three lines here. There's a solid bold one. This shows the total density. Actually, the total gas density. Now this dashed line shows the dark matter density along the same line of sight. This is delta x, is capital, and this is delta b. And again, they're not the same. They're kind of tracing each other on large scales, right? They look very similar. But on small scales, you see the small fluctuations in dark matter, which you don't see in the gas. It is a filtering scale thing, right? These fluctuations are suppressed. I mean, they didn't grow. So dark matter grew those fluctuations and gas didn't because of this filtering scale. So again, you see this filtering scale in action. And then this thin line is a spectrum. It's tau, actually, e to the minus tau that you observe. Even e to the minus tau goes from 0 to 1. So you see this, whenever the density is large, you have a lot of absorption. You see this very large absorption feature. Right? Whenever you have peak of density, you have dips in the optical depths. But they are somewhat shifted because the optical depths, we are looking in redshift space, on velocity space, where this is in real physical space. Right? So for example, this peak of the gas density causes this absorption, but it happens at a different place because of this velocity dispersion. This means, because of the peculiar velocity, this means the gas in this density peak moves in this direction with the velocity, which corresponds to the shift of the wavelengths. So again, this peak gives you rise to this feature, this peak gives rise to this feature, etc. So if you actually look carefully, you can make this one-to-one match between a peak in gas density and the absorption feature in the Lyman alpha spectrum, except again, they are not exactly the same velocities because of this peculiar velocity shift. They are sometimes shifted. But there is more or less a one-to-one correspondence between them, and I think we can stop there here. Oh, okay, one more. Why universes are ionized, right? So I promised to tell you that. So if we now go back to this equation, right? And what I want to do is just to plug in some rough numbers, right? So I know roughly what the mean density of the universe is. I know roughly what the size of those density peaks that produce absorption features are. It's about 100 kiloparsec. I know the temperature of the IGM is 10,000 degrees. So what I do is just put all those numbers in. And I also remember from this blue versus magenta plot that about half, or roughly comparable amount, is absorbed versus transmitted, which means that my optical depth is somewhere between 0.5 and 1. So if I take average optical depth over the universe at redshift 2 or 3, it will be in this range. So I now take this equation, plug in all the numbers, right? And what I find is that if my x is 1, if the universe is neutral, then my optical depth will be 7 times 10 to the 4. At redshifts A, 4a equal 1, a is 1/4, which means redshift 3. Right? So if the universe was neutral at redshift c, you would see not a single photon in those spectra. Right? It would be optical depth 10 to the 5, but nothing gets through. Right? That's like looking through the wall. So the fact that we actually see transmitted flux and the tau is that low means that x has to be absorbed of 10 to the minus 5. So the reason why the universe is ionized, the reason why we know that the universe is ionized is because of this, because we actually see Lyman alpha forest. And if it wasn't that highly ionized, there wouldn't be anything. The trees would be just so dense that there would be a single photon going from that quasar to us. Right? Everything would be completely black. Okay, so then we'll stop with this, and tomorrow, right, or tonight, we'll talk about the temperature. As I said, you're supposed to ask questions during me talking, so then I don't accept questions afterwards.